All right, so now I want to re-explain what a soup is intuitively using the definitions in an illustration that I thought of in the D hour, but I didn't think of in the C hour, kind of prompted by Katie's questions. So I'm looking at a graph of n against 1 minus 1 over n against n. It's a sequence, and you can see that from our classwork that the soup of this sequence is 1. And I don't think anyone has trouble understanding that that's the soup. It's not a max because the max has to be attained and the soup does not. So 1 is never attained, it's just reaching it as a limit. So definition number 1 is the soup of part 1 of that definition is that a soup must be an upper bound. So I'm going to throw up an upper bound here. There's my candidate, a candidate for the soup. There's an upper bound. But the second part of that theorem or that definition says that we also need that the soup of A has got to be the best upper bound. So it's got to be lower than or equal to, it's got to be an upper bound, but it's going to be lower than or equal to any other upper bound. So here's another upper bound, and my upper bound's got to be lower than that. And if I start taking that green upper bound down, my soup is always going to be lower than that. And my upper bound can't go below the soup because that's the best of the upper bounds. So that's definition 1, and I think we fully seem to understand definition 1. Definition 2 is a little bit more trickier. So for each epsilon greater than 0, there exists an x belonging to the set such that s minus epsilon is lower than x. And this bothered Katie. Let's see if I can draw some pictures here to alleviate that. So here's the soup. We already know it's the soup. I'm going to drop that soup by epsilon. So I'm just going to move that epsilon down a little bit, that stick. What happened is s minus epsilon is no longer a upper bound. In fact, I have some x values that have escaped. They've escaped the bar. And so that's what this is saying, that something's the soup because if I lower it by any little bit, there's going to be some x's that rise above it. And so you can pictorially see that there's some x's that rise above it. And no matter how low I made this, if I dropped it even less, still far out enough in the sequence, I would find members of the sequence that have escaped the bar. Well, you really need to think about all conditions. This is probably where I used to fall apart the most as a student. But what if the soup of A is actually a max? What then? Let's take a look at something like 1 over n, where the soup is the max that's attained. So the max of the set is 1. And if I drop by a little wee bit the soup, which is the max as well because it's attained, I get this dash bar, and you say, well, there's no x's that have escaped. Well, yes, there is. There's one right there. The max itself, which was in the set, is no longer covered by the bar. And so with a max, it's almost easier. You automatically have the x's given to you by the max itself. Okay, so that should give you a better idea of the second definition and even the first definition. It's a nice idea to think of this as bars. Now, if you have a bounded set, you would have a bar on top and a bar on bottom. And the inf and the soup would be the lowering and raising of these bars until you've squished the entire sequence within it, and it's the best squishing. And these are officially professional words that we use in mathematics, squishing.